Hello there, everybody. Mr. Eiler back here with another exciting physics lecture for you. Today is waves number 3, and what we're going to talk about today is the Doppler effect. Probably heard of it before, and you may even know what it is. If you do, this should be really easy. If not, that'll be good. This will be something new for you. Once again, we will not need equation sheets today, but a couple colors may be helpful. Definitely not necessary, though. So here we go. To start off, let's pretend there's a person singing a note. And they're keeping the note the same, the pitch of the note the same, and the volume, and the note's going out in all directions. Okay? What I've drawn here is a representation of that wave. And let's think about each circle being the crest or the top of the wave, and then in between it goes down to a trough, and then it comes back up to the top at the next blue line. Okay, so just like ripples on a pond, their voice is going out. Now their voice is going out in three dimensions instead of just two, like on a pond, but drawing it this way helps us kind of visualize it. All right? So now let's think. The red arrows represent the wave speeding out from this person in all directions, and the wave pretty quickly is gonna get to that person standing over there on the right. And what they're going to hear is whatever note that person is singing. Wah! Something like that. And think about the waves zipping by this person, and they'll hear the note. Now, remember, just like we talked about, the wave that's going towards them is not a transverse wave like the wave on a pond. It's a longitudinal wave. Think of that big air gun that we used, the Airzuka. It's a compression wave that's going towards them. But we're going to draw it, think about it this way and draw it this way because it's easier for our brains. All right? So they hear a note. Fantastic. That's good. No big deal. Everybody should be okay here. Now I'm going to change it a little bit. Now that person is going to be running, the singing person is going to be running towards the person who's doing the listening. So now check out what happens. The red arrows still represent the waves going out. Let me draw a couple more so we remember they're going in all directions. But look at what happens. The person who's yelling or singing is running towards the other person. So what happens is those waves get squished together just a little bit. So look at the wave length of the waves. The distance from the crest to the crest is just a little less than it is on the backside, behind the person. All right? So now remember, you can't run as fast as sound goes. Well, you might be able to, a couple of you, but most of you can't. I'm kidding, nobody can. But the sound is still going out way faster than the person's running. So the sound is going to get to the listener quite quickly still, but it's going to be a little closer. So instead of singing or hearing the note, wah, they're going to hear, wah. They're going to hear a higher note because the wavelength is a little bit shorter. Okay? So the wavelength has gone down a little bit, decreased. Now here's what's crazy. The person running is still singing the same note. The person if someone's listening in front of them, they're going to hear a higher note. Think about a person behind them, back here. They're going to hear a lower note because the wavelength is stretched out. It's increased a little bit. Okay? How's that? We doing okay so far? Good. One other example. Let's go back to the beginning with the person stops running and starts singing a note. Okay? Person in front and behind will hear the same thing. Now check it out. I'm going to change something. Let's have the listener run towards the person who's doing the singing. All right. Now this is just a little different because the wavelength is the same, but it goes by them faster. Okay? So each crest goes by sooner. And the crazy thing is, if we go back to our second slide, each crest went by sooner as well. So the same thing happened. All right? In this third case, what we get is the note goes up if you're running towards the person. Now, if you're over here and you really hate their singing and you're running away, guess what? The note's going to go down. Okay, so we have two examples of the Doppler effect. The Doppler effect is when the tone or the frequency or the note changes because either the source of the sound is moving or the person receiving the sound. So there's two cases we can make the Doppler effect. All right? That's about it. Your quiz for tomorrow is going to be to explain that in your own words. All righty. Sounds great. We'll talk to you tomorrow.